All right, welcome back. So today we are going to graph one more. We have seen a graphing exponential growth where the graph grows from left to right. We have seen graphing exponential decay where the graph goes down, less positive or less negative from left to right. Today we're going to graph what are called exponential equations with the letter E, and that's a constant that we are using. And that E, it has been named for Euler, famous mathematician. And if you don't recognize this, this is something that we're going to be using later on when we deal with compound interest or interest compounded continuously. And its value is approximately 2.7. We're not going to worry about all the logistics of it. We're just going to remember that E is approximately 2.7, and that's what we're going to use because it is an irrational number like pi, so it does go on forever without repeating. So like we use pi as 3.14, E is going to be 2.7. So when we deal with our graphing, when we do the -1, 0, and 1, and we go ahead and we make our tables with A over B, A and A times B, if we were to use 2.7, these would be the values that we would get if it was just 1 times e to the x. Okay, well let's look at this. Our first one, -3 e to the x plus 1 minus 4. Again, remember e is about 2.7. So we're going to set up our table with -1, 0, and 1. A is -3, B is e, and C is -4. Now I'm noticing that B, the value E, is 2.7. That's bigger than 1. So I know to expect that my graph is going to be like an exponential growth graph. It's going to get more positive or more negative as I move from left to right. So 0 is going to be our A value, which is -3. -3 times 2.7 will give me -8.1. And -3 divided by 2.7 will give me -1.11. So this is where we start our table. After this, you should feel fairly comfortable since you've done the exponential growth and decay. The x's, we're going to go ahead and subtract 1 from them. So we get -2, -1, and 0. The y's, we're going to go ahead and subtract 4 from those. So -5.11, -7, -12.1. That, of course, is also our horizontal asymptote, y equals -4. And that's it. Then we're going to go ahead and graph it. So -4, I have -2, -5.1, -1, -7, and 0, -12.1, which is off the graph, but I'll just kind of estimate. This is an exponential growth problem specifically using E, so that means it's going to get more negative from left to right or more positive, depending. The domain is all reals, and since the curve falls below that horizontal asymptote, the range is always y is less than -4 in this case. Okay, next example. 3 multiplied by e to the -2x. This one looks a little bit different because in the exponent I see -2 times x. Well, let's see how we can deal with that. The first thing, I'm going to set up the table. A would be 3. A times e, or A times 3 times 2.7 is 8.1. And 3 divided by 2.7 is 1.11. The only difference I see in this problem here is that I need to deal with the exponent. I do the opposite to the x's, so these x's, I'm going to divide them by -2. -2, we might have to remember back in our transformation unit that when you change the x's on the, when you change the signs on the x's, it's going to reflect over the y. So that's going to look a little bit different to us. So let's see, I get +1/2, I get 0, and I get -1/2 for these values here. It looks like I don't change anything with the y's. And since the c value is 0, our horizontal asymptote is still y equals 0. So let's go ahead and graph that. Y equals 0, positive 1/2, 1.1, 0, 3, and negative 1/2, 8.1. And it's strange, I'm kind of moving from right to left this time. And from right to left, it gets bigger. So this is almost changed to an exponential decay problem because of that negative in the exponent. Something to be aware of, something to kind of pay attention to, that even though, yes, this was supposed to be an exponential growth, that exponent that changed the x values ended up converting it to an exponential decay problem. So horizontal asymptote, like we said, was y equals 0. The graph falls above that, so y greater than 0 is our range, and our domain is always all reals. All right, our last example here. I already have the table set up, the basics, since a is 1, and I have a times b, and a divided by b up there. Let's start with the easy one. I see that c is positive 1, so my horizontal asymptote is 1, and I'm going to add 1 to the y's. I can do that. Now to the x's, we're going to do the opposite. So that means that the first thing I'm going to do is I'm going to go ahead and divide by negative 0.75, and then I will add 2 because I'm sort of unwrapping it. And so when I take negative 1 and divide by negative 0.75 and I add 2, I get 3.3. When I do the same with 0, I get 2. And when I take 1 and do that, I get a positive 67. Positive, no, 0.67, excuse me. Okay, I noticed that negative up in the exponent, so I should be expecting that this is probably going to change to what might look like a decay graph. I put the horizontal asymptote on there. 3.3, 1.4, 2.2, and 0.67, 3.7. Maybe it's around here. We're just estimating. And yes, in fact, it looks like an exponential decay graph because of that negative in the exponent. Domain is all reals. The graph falls above the horizontal asymptote, so y is greater than 1.